Hello everyone. Today we have Lasse, who will be talking about index Merkle trees. And welcome everyone, and welcome Lasse, and the floor is yours.
Thank you. So I'm Lasse. I'm from Aztec, and we're talking about indexed Merkle trees for this session. So the presentation agenda will be as this. We're shortly going over what is Aztec and why do we even have interest in these trees. Then go over our legacy nullifier setup, how index trees make sense for us, and some of the intuition of why or how they work. And then essentially we end up with profit by having smaller circuits at the end. So we can shortly for Aztec, for those that don't know, we're working on building a layer 2 that's having private smart contracts. So this means that we also end up having a lot of private state that we need to deal with, and nullify is an important part of this, as we'll see shortly. So we need some way to efficiently prove that all of the data is up to date. And we need to do it very efficiently because a lot of this stuff needs to happen on user devices. So it cannot just happen on a huge server somewhere. So we've been always trying to find some ways to do the proofs more efficiently. Sometimes it's by having new proof systems where the cryptography has just gotten better. But this type of change here from the indexed Merkle tree is more of a engineering fix or feature than actually finding a new cryptographic primitive. So a key takeaway from this is also that you can contribute to making the proofs more efficient, even if you don't necessarily get all of the cryptography. If you can just figure out, hey, what if you do this on a specific part of the setup or the stack? So we'll be looking briefly at the two trees model and why it exists. This is very relevant for why we're having these trees at all. So if we are taking a thought experiment and saying our roll-up state has a state tree where for every slot we have some value and it has shoved through this route. If Zach make a transaction, he has a transaction, it updates some value in this tree. It could be a balance update, it could be whatever. So he inserts a value, we now have it in this roll-up block state tree. Time flies by, all of the rest of the state have been, or more of the state have been filled out, so there's a lot of state values at different slots. Eventually, Zach figures out that, hey, he wants to use some of the funds that he deposited in somewhere or change some value. If he's doing this transfer on the same storage slot, you could see that so this value was 300 before, so it's 600 now. He's updating the value, and we can now see that, hey, someone changed this value. Even if all of these values are encrypted, if it's happening on the same storage slot, you can just see that, hey, something changed. And if we're dealing with something like a transfer, someone will there will be changes two places, the guy that are sending funds and the guy that are receiving funds. So we can start making profiles if this is something we can do, and having just one roll-up state tree. So yeah, this was just what I mentioned. If data encrypted, if it's deterministic what the slots are, you can still figure out some information about the recipients and the guys that are using the system. So the fix is essentially a bit of spoiler, introducing these two trees. So what if we have our state tree, but what if whenever we're doing an update to a specific slot, we never write to that slot again? So just simply don't update slots. To address to have this actually be possible for us, we introduce a second tree. So we have one tree that is for data, so you're storing commitments to data, and you have a separate tree that is for indicating that this data had been consumed or nullified. It's often called a nullifier tree. So yeah, in terminology, we have commitments in one tree. So a commitments tree. A commitment is some, like, could be a hash of some data that you're putting into this tree. So only the hash is there. And if you know all the contents, you can spend that commitment. And when you're spending it or consuming the data, you emit like a nullifier, such that if someone tries to spend the same data later on, this nullifier will already exist, so you will catch it as like a double spend. So if we're drawing this out, we'll have these two trees, where on the left we have this state tree, and on the right we have a nullifier tree. So when Zach is like updating his value, he will just like insert a new value into this the state tree and nullify the old one. And the nullifier doesn't have a clear link to what it was nullifying that is like visible from the outside. So from the outside, you would just see, okay, some data was spent and some new data have been inserted, but you don't know really learn anything more than that. So yeah, we insert the value in the new slot, and we create a value in the nullifier tree just to indicate this had been consumed. Something that's very important for this part to actually work is that you can like deterministically generate the nullifiers from some of the original state. So say that we have a case where this isn't, we just use nullifiers as like a random piece of data, like fully random, then you don't know, like if I'm trying to spend the same data again, I could just pick a different nullifier and then I can perform double spends. So you need some way to deterministically compute it. Often this is that as part of the original state, when you're inserting these like data blobs into the commitment tree, you have some secret in there that you are using to compute the nullifier. So if you try to use it again, you will hit the same nullifier. So that was just having these two trees. One is for nullifiers. If it what? Was there a question or? I'll just continue. So we were having these two trees, one of them being our data tree and one of them being our like nullifier tree, where okay, this is just to keep track of what have been spent. So in this case, we have this tree that has as many leaves. The nullifier tree will be a sparse Merkle tree, which has as many leaves as possible values. So let's say this is our sparse nullifier tree when we start out. Everything is set to be null. So there's nothing, and then no data have been nullified. In this case, yeah, we can have like 8 elements. And if you want to check that a specific nullifier is in the set, you just try to like go down essentially the tree to the specific index. Like the index is the value of the nullifier in this case. So if you want to see that there's nothing in there, you go down to see a null. If you expect it to be something, it could be like a Boolean, just the value itself, or hey, a flag that this thing was already spent. Yeah, this allows us to prove that there was also a null at the point in time. So if I can go like all the way down, we can also go up and go from like the nullifier that we want to prove is not yet spent and compute the root. So this is like a Merkle path membership or Merkle tree membership, where we're essentially saying if we want to show that like the value 2 is not in the nullifier tree, we can start at like index 2 in this case, and then we just start like doing normal Merkle path or Merkle membership proofs from here. So we do a couple of hashes. If we're getting to the same root as like the current root, okay, we're good. There's no value in there. So we're not overriding something that was already there. Everything is nice. So what is the issue with this? The main issue is that for this tree, it was super tiny. We had a tree of size, like tree depth which means that it could only contain 2 to the power of the depth elements. And when this was like all the possible values, this means that for so small trees, you could have like a couple of transfers and then you don't have any more in there. And if you're having these values, you want them to span like a large domain, just as that it's harder to, that you have more space to be in there, or you can have more, them seem like more random. So when we're dealing with this in like a real world scenario, so for people that don't know, Aztec had this product that was called Aztec Connect, which allowed you to do private transfers and so on. And in that setup, we were using these fast Merkle trees. And to make it like practically work, we needed to have a tree of depth 254, which means that we need to do a lot of hashing to do these membership checks. So for every time we wanted to check that, hey, you're not double spending inside something, you would first do the membership check from that, hey, the value is null at the moment, and then you would insert it and compute the new root. So you end up doing 508 hashes for every insertion. So this becomes an issue when you start doing rollups of larger batches. So in our case, it was not fully 1,000, we were around 900 transactions in a batch, but every batch could produce like multiple nullifiers. When you have these 500 hashes per nullifier, it quickly adds up, being like 1,000 hashes per transaction and 1,000,000 hashes for the entire rollup. Overall, this just means that the rollup circuit itself has a shitload of constraints, and you need a very powerful machine to actually compute it. So what can we do about this? Because this is our main bottleneck at the moment. And when we are moving to have smart contracts instead, it will only get even worse, as now there's more state to deal with. So we needed to figure out how to do something better. And the initial idea is just, how can we get away with doing less hashing? And can we do it such that we can still perform these non-inclusion proofs to make sure that you don't double spend anything? And there's a pretty simple idea that we would have liked to have figured out ourselves, but it's also okay to get some help. So was this idea from David that, hey, what if you, and he's saying this, that I have this new idea for a Merkle tree. What if you store a linked list of the leaves, such that they can be like ordered numerically, so you can more easily perform these non-membership checks. So we go over this idea, and this is what we've called indexed Merkle trees, as you just keeping track of the indexes. But you could also think of it as like a successor Merkle tree. So the key idea is, what if we use a linked list as all of our nodes, and then we prove that something is not in this list? So if we have a linked list of sorted nodes, and then you have like node 1 is pointing to node 2, which is like its successor or the next highest value. So the highest, the smallest higher value essentially. And when you have this like link, it means that if node 1 is pointing to node 2, you know that there's nothing in between them. So if you start having actual values on these, say we have 1 and 10, then we know that, okay, there's nothing in between. So 2 to 9, they don't exist in this tree at all. With this idea, and so the idea is taken also from this paper. But with this like idea at hand, we can start designing a more interesting tree that is a bit more complex to use than the sparse tree, but gives us some nice properties. So the idea is that for all of the leaves in this index Merkle tree, we'll keep the value and essentially a pointer to the successor, and then we can just append these as an append-only Merkle tree. So it will essentially be used as a list. You just insert into next available spot, and then you need to go back and update previous leaves. But if you have this at hand, okay. So the initial state will essentially look like this, where you have your tree, but instead of having just these indexes and all the values are null, we now have like 3 values for every node. We have the value itself, and then the pointers to the next to its successor. I think someone needs to mute or so this is the initial state, and while all of these are marked as 0, the first 0, 0, 0 is like a special class here, as it both the minimum and the maximum value. So if you want to insert into this tree, if we want to insert 30 for this case, we insert it into the next spot. So this will be index 1, and then we need to update the its like predecessor, and the predecessor in this case will be the first value. So it will now be pointing. I don't know if you can see my mouse, but if you can see my mouse, you can see that hey, index 0 is now have value 0 is pointing to index 1 with value 30 as its successor, and 30 is pointing to 0, 0 as its successor. If you're pointing to 0, 0 as your successor, it just means that you are the largest value. So you're essentially pointing to the beginning. So this is how we can do like one insertion. If you're inserting again afterwards, say we're inserting 10. So when we are inserting 10, we first need to do this check that, hey, 10 is not already in there, which we would be doing by jumping to going down the tree here, showing that we have this node in the set that has value 0, and the next value is value 30. Okay, 10 is between 0 and 30. So we know it doesn't exist in the set already. We can do this like range check essentially. And then we just insert it and update the predecessor to point to 10 now. So you can see the first value is now pointing to 10, and 10 is pointing to whatever was the successor of its own predecessor. That might be a bit hard to figure out the wording here. So essentially, when you're inserting, you will take the values from the node you have inserted right after and use them as your new successor. So what you are pointing to. So if we're jumping over them like as this linked list, we start at 0. We can see that, okay, we should jump to index 2. So that's 10. And from there, we jump to index 1. So that's 30. So we have 0, 10, and 30 in this set. Then we can keep on doing these insertions where we, again, just same flow. Does it mean that every update can have max and modify to nodes of the tree? So we essentially, yeah, we have that every update does this, but you can also do a batch insertion that will show. Yeah, I think it should actually be in just a second. Where we can go over how you can do some of these batch insertions. So essentially, to do this insertion, you need to know the full data of the your predecessor. So in the old one, you just need to come with, hey, this is my nullifier. Now you need to know some more information about, hey, this is my nullifier. Here was some of the earlier stuff, and I'm not in this set. So you need a bit more access to information, but the stuff that the circuit needs to do to perform the inclusion can be can be easier. And to do this, or can be less computational. So when you're doing the inclusion proof of node 10 in this case, we essentially do it just as before, like Merkle membership, all the way up to the root. Okay, node 10 is in there, and we know that like 10 is also pointing to 20, so there's nothing in between. So yeah, this was just refresher from earlier. If you had 1 and 10, there was nothing in between. So when we have 10 pointing to 20, we could insert any value, or any value between 10 and 20 do not exist in the set already. So all we need to do to membership is just, okay, the smallest of these nodes, so one path of the tree and the values of this node. So if we do, it should be 11 to 19. So the idea is, if we wanted to insert, like, do the inclusion or prove non-inclusion of 15 from this case, we have our current value was 10. So we need, like, 10 should be less than the value we're trying to prove is not there. And the next value should be larger than. And 15 is more than 10. It's less than 20. We're all good. In this case, we could insert it, and yeah, we're doing this through 2 range checks then, to prove this inclusion and the Merkle path. So the nice thing by having this case where we can just append new nodes is that we can change the size of the tree. So instead of having this like sparse Merkle tree, but we had of size 254, we can have the same size as our like commitment tree. So all of the data can only be nullified once. So we can make the nullified tree the same size as this data tree or the commitment tree, which in our case was 32. So in this case, to do the inclusions, we can just need to do like 32 hashes up and 2 range checks. Then you have done the non-inclusion. That's a lot easier than doing like 254 like hashes. But we also have a bit more nice ideas around this with because you're not doing like random insertions anymore, but we're doing like structured insertions. You can essentially compound multiples and insert a subtree at once. So this means that you could do a batch insertion. And when you're doing this batch insertion, you have some of these hashes that you needed to do normally. Now you're essentially amortizing them over all of your batch. So you can get away with doing like way less hashes overall if you have these batch insertions. So if we try to insert a batch, yeah, so we are going from the tree we had before, and then we're saying we want to prepare a subtree and insert 35, 50, 60, and 15. And so inserting this subtree marked with the gray square. Initially, we will need to point to like all of the update what was already in the tree. So these like it's sometimes called like low nodes or the predecessor. So in this case, when we're inserting 35, our low node would be the node 30, marked here with green. So we need to update that value, or update its successor to be 4 now. So the index in where we're inserting is 35 value, and we need to set the values of our 35 node to be 0 and 0, as 30 was the largest value we had before. So we are doing some updates here on the existing tree and some only in our subtree. After this, we can insert 50. 50 is larger than 35. So we need to update stuff that are already in our pending insertions. And for 60, same stuff again. We update values that we have inside our batch insertions. And then when we're getting to 15, we are doing the check all the way from 10 to 20. We're doing this like updating the node with value 10. So throughout this process, we had to update some of the values in the existing tree and change values in our like pending subtree. But when we have been going through all of these, this process and updating the pointers also in our pending tree, we can essentially just insert the whole subtree at once. So we save a lot of hashing, as you don't need to hash all the way up for every node now. You're just doing once for that entire subtree. So if the larger the subtree, the more savings you're getting from here. Yes, this was essentially how you like insert doing these batch insertions. So I hope that helped a bit on the question from earlier in Rico. Did it help on your question?
Yeah, it does. Thank you.
Okay, perfect. So I think this is actually like the planned ending of this. What we were drawing out. So the main thing that we are really winning from here is saying, okay, what if we could introduce some structure to how we do like nullifier trees while still computing, still having the same some of these while still having the same properties to, hey, we can do non-inclusion checks and hopefully do this pretty easily and cheaply. Yes, the main thing was introducing some more structure on how we can do these checks. Essentially, yeah, because if we have the more structure we had, the more information we could like deal with outside of our circuit. So finding these like predecessors, we can do that. All of that stuff we can deal with outside the circuit. But then have that the circuit itself need to compute less information. Yeah, I think this was essentially what we had planned for this. We have a Jupyter notebook with some examples that people can play around with. I will probably add it to the slides, and then when they get published, people can play around it with it if they want. Is there any questions related to this, or something that was like super unclear from how I described it?
I have a question, if I can maybe just ask here on the voice. Thanks for the presentation, by the way. It was very nice. So maybe you could share where that information is stored, like who has access to what information, and I mean the root and the leaves.
Yeah, okay. So in when you're dealing with these cases, so the commitments and the nullifiers are all broadcasted on chain in at least in our case, which means that any node that have access to L1 state could essentially rebuild these trees. So say you're running a node. When you see these commitments coming in, you just like add them. It's append only, so you just add them into the tree. When you see the nullifiers come in, you like also add them into the tree, but you need to do these like small updates to the state as well. And then you can compute the state locally and see that, hey, you're getting the same thing. The idea is that this circuit and should make sure that if you're doing updates the same way, this is the result that you set it up with, but you can perform the checks locally as well.
Got it. Makes sense. So basically everything is in plain text, right?
Essentially the nullifiers are essentially in plain text.
Yeah.
So the nullifiers just seem like random garbage that you're spitting out. You just need to make sure that if you try to nullify the same commitment, it will always produce the same nullifier. And for commitments, you will just see like the commitment itself, not the data in it. So the data in it will be held by like the user that owns that data.
Of course.
But you can, so if I like have some funds in the system, everyone can see the commitments, but they don't know whose commitment this is. And I have the data that is like inside those commitments. So when I want to spend it, I just prove that, hey, I know the data that is part of these commitments. Here are the nullifiers, and they are not already like have not been spent before. And then the nullifiers are broadcasted.
So basically, as a user, when I want to make, I want to spend something that hasn't been spent before, I would ask, assuming that I don't keep the state of the tree, like all the leaves myself, I would ask some node for the leaves that are needed to reconstruct the Merkle path.
So you would, you do that for your like your commitment data. So you would probably hold that data yourself. So when you're doing commitment inclusion proofs, they don't need to happen with the current state. The nullifiers are sort of ensuring that, hey, this thing haven't been spent before. So you can do inclusion proofs for your commitments on like old state, which means that you could, when you are receiving the funds, you could just store the path and put it, like say it's on your hard disk. So you have the information right at hand. And in our case, we have that you are doing the inclusion proofs for your commitments. And then you just have the values for the nullifiers. And then there will be this, the idea is that we have a federated proving network, which will essentially be, okay, they see the nullifiers, and they will then be able to find, they have the full state, so they can just, or the full nullifier tree, so they can find the predecessors and perform the insertions.
Thanks.
Doesn't it add more? Yeah, it adds some more performance requirements on the node side, because you need to know where these prior like nodes were. So in the sparse Merkle tree world, you only need to like know the nullifiers that you are inserting, and so you have like 32 bytes of information per node that have been inserted. And in our case, you need to know also, the next value, so you have a bit more information per node. So you have some more stuff there, but you have a lot less hashing to do when you're doing updates of the trees. And since we're doing like snark friendly hashing, it can quickly add up if you suddenly need to do like factor of 10 less hashing. On the second question, how does the search happen for finding the new nullifiers for non-membership brute force? So essentially, you you could do brute force is probably one of the easiest way to do about it. Elsewhere, it is essentially because it's a linked list, you can essentially do like any of it's almost like a sorted linked list that you can have. So you can just do any like a binary search in the data if you want to do that. Because like all of the leaves, so you can just binary search your way through it. Hope that helped a bit. May I ask if there's an implementation of this variant of Merkle? Yeah, we have an implementation. Where is it easiest to send links as they are available for people? Just to add them at the end of the slides. How can we do a linear search in the circuit to find an? So you don't need to do the search inside the circuit. You can do the search on the node, and then this for the circuit, you just say, hey, here is the low node, and prove that this is actually the low node. So you're doing all the the complex stuff, or as much of it as possible, doing that outside, and then you just say, hey, here's what should be the answer, and prove that it's the answer. But we have an implementation of, I'll find a link to it. Otherwise, it can probably be a bit hard to find. But in our crypto library Berittenberg, there should be an implementation of it, and there's also some implementations of some of the other ones, or the standard one. Cool.
Could you also maybe explain again why the requirement for depth of 254 is not needed anymore, and now you're using 32?
Oh, yeah, okay. So in the 200, you essentially needed to cover the entire space that your nullifiers could land in. So if you're doing nullifiers through hashing, you would often do it to say it's Peterson hashing you end up with just a field element. And if you want to do it so that it's very easy for you to do a non-membership, you can use the value of the nullifier as the index itself, because then you know exactly where to look up the value. But then you need your tree needs to be large enough to contain all of the possible values. So that's why you had this large tree, and we can live with this smaller tree because we can do this append only, and then we're just saying, okay, the node will find the leaf you need outside of the circuit, and then you just prove that if you were inserting 15, for example, earlier, that we had this node that has value 10, the next one is 20.
Got it.
So we only needed as many, our nullifier set practically. So the set of possible nullifiers is the field size. So that's 2 to 254. But the set of possible nullifiers is smaller, as you can only have one nullifier for every commitment that have been inserted. So you will never actually fill out the entire thing. And the range cost should be negligible. Yeah. So the range cost in this case, you could say that as long as the range cost, we had 2 range checks. So as long as they are cheaper than 100 hashes, then it's cheaper in general. And then if you start doing the batching, then it becomes even cheaper. Okay. But yeah, I'll add some of the links to the code at the end of the slides before they go up. Any questions here at the end, or?
Okay. No more questions? Okay. So thank you, Lasse, for the great presentation. Thank you so much. And thank you everyone for attending. And yeah, so see you next time.
Okay.
Thank you. Bye.
Bye-bye.